And we were discussing relationship between voltage and current for a resistor, for sinusoidal alternating current. So we related so far plots of voltage and current, and we see that they are proportional. When one gets zero, when current gets zero, voltage is zero as well. When current assumes the highest value, voltage assumes the highest value as well. Let's now take a look at the phasors. So, and actually, I will at the same time I will look at this as using complex analysis. I will think about complex current and complex voltage. I recognize that voltage across the resistor is equal to the imaginary part of the complex voltage, and current across the resistor is the imaginary part of the complex current. R is a certain real number. So I can write that this is imaginary part of complex voltage, and if R is real, then it doesn't matter if I have this real inside of imaginary part or outside. So now I can from that conclude that complex voltage is equal to resistance multiplied by complex current. From that, I can immediately conclude what is the complex impedance of the resistor. Because complex impedance is a number which relates what with what? Which voltage with which current? You are right. Not peak. Which one? Yeah, I mean, here's the problem. I told you that you will have a problem because you will start confused what are we talking about. So which current and which voltage are related by complex impedance? Let's recall actually everything. So let's start with this. Which coefficient relates complex current with complex voltage? A what? No. Complex impedance. Now, which coefficient relates peak value of the voltage with peak value of the current? Impedance, correct. Which coefficient relates root mean square value of the voltage with root mean square value of the current? I mean, because this is where the problem with physics is. We don't know what is what of what. And if we don't know what is what of what, how can we relate those? First, we have to know definitions, what we are talking about. And then when we know what we are talking about, we can use formulas. So, root mean square value of the voltage is related to root mean square value of the current by a what? Not average power. Not phase angle. Impedance, correct. It's also by impedance, like peak value. Peak values are related by impedance, and root mean square values are related by impedance. Now, how instantaneous value of a voltage is related to instantaneous value of the current? What is the coefficient between those two? A what? I? What is I? You mean we multiply current by current to get voltage? Current by resistance. Is it true? Do we multiply current by resistance to get voltage? No. Only for a certain type of elements. Which type of elements? Only resistors. Only for resistors, current and voltage are proportional. I mean, that question was kind of tricky because we don't have a coefficient which relates current with voltage. So we don't have a universal coefficient which will relate instantaneous value of the current with instantaneous value of the voltage. Recall that in a capacitor, we have to calculate the derivative of voltage in order to get current. In an inductor, we have to calculate the derivative of the current in order to get the voltage. Only in a resistor, we multiply current by a number to get voltage. All right, let's go all over. So root mu square value of the voltage and root mu square value of the current are related by impedance, correct. Peak value of the voltage and peak value of the current are related by impedance. Complex voltage and complex current are related by complex impedance, correct. And current and voltage are related by not related, all right. They are not proportional in general. They are only proportional in a resistor, and then it would be resistance. All right. So here we have an expression which relates complex voltage with complex current. Here we see that in a resistor, complex voltage is proportional to complex current. What do we call the proportionality coefficient between complex voltage and complex current for an element? Not resistance. Complex impedance. What's the conclusion? That resistance of the resistor is equal to the complex impedance of the resistor, correct. So complex impedance of the resistor is always equal to resistance. How about impedance? Is impedance equal to resistance? Yes, we found it yesterday. Yesterday we also found it. So for a resistor, impedance, complex impedance, and resistance are equal. All right, now, if we have complex impedance, how to find impedance itself? What do we have to do with complex impedance? It's a simple procedure. We take an absolute value of it. Okay, so if we take absolute value, let's say that I have a resistor which has resistance 10 ohms. And if so its complex impedance is going to be 10 ohms. What is absolute value of this complex number? 10 ohms, correct. In other words, if impedance, impedance itself is going to be also equal to resistance, which is consistent with this what we found yesterday, because yesterday we came to that conclusion that impedance is equal to resistance. Also yesterday we came to the conclusion what is the phase angle. What's the phase angle for a resistor? 0. How do we see it from the plots? Because they are proportional, there is no phase shift. They are always in the same phase. When one has phase 0, the other has phase 0. When one has phase pi over 2, the other has phase pi over 2. Now, how do we actually calculate phase angle from complex impedance? I mean, these are the two formulas which are really very good to remember. How to find out impedance and phase angle from complex impedance. Well, I will have to take ratio of imaginary part of complex impedance over real part of complex impedance. What is imaginary part of this complex number? Let's say 10 ohms. Yeah, so if it is 10 ohms, real imaginary part of this number is 0, correct. And real part is 10. Yes, so we'll have 0 over 10. Tangent phi is 0 over 10. Angle of, tangent of what angle is equal to 0? 0, correct. So we see that the phase angle is 0. All right, let's now draw the two phasors. Yeah, so let's say at this instant. And again, I already skipped drawing the circle. But first of all, indeed, I would, in principle, I should draw a circle equal to the, with radius equal to the peak value of the current, then draw a horizontal line and find where the horizontal line crosses the circle, and select one which corresponds to the rising current. I skip that. I hope that you already comprehended it. Now, how should I draw the phasor representing voltage?
It should be going up like that.
Right, it should be parallel. Yeah, the two phasors have to be in the same direction. Yeah. Over here, we actually see that the phases agree. Yeah, because where's the phase? Phase is the angle on the phasor diagram. It's the angle between the horizontal axis and the phasor. So both have the same angle. All right, so as time passes by, both current and voltage oscillate, and the phasors rotate together counterclockwise.